Yeah, I hope you all have enjoyed the interesting conversation so far. And let's start the afternoon session. It's my great pleasure to introduce Dr. Nathan Crock. Nathan is an insider here. He founded this event in 2008. Currently, he's a manager at the Premier Blue Cross and also affiliated faculty member at the Scientific Computing. His career bridged academic research and industry practice and creating innovative solutions. Today, he will share with us the challenge and hopefully solutions also to building agentic web. Let's welcome Nathan.
Thank you very much for the introduction, Dr. Liu. And it's nice to be speaking with all of you. So yeah, I'm going to be exploring some of the core challenges here in decentralized multi-agent systems, which is going to be the underpinning of what we would think of as the agentic web. So I'm going to build up to it here piece by piece. So let's start with agentic foundations. So a language model itself is the engine behind agents. They receive a query and a list of tools. And the language models now, the vast majority of these foundation models, create a directed acyclic graph of how the tools should be orchestrated and strung together to accomplish the task. Okay. And what happens during runtime with these types of agents is a lot of sophisticated engineering efforts here, dependency resolution. So maybe a tool fails, a new tool is needed. It must be injected into the graph. Where and how is it injected? And how do you ensure that the proper inputs to subsequent tools are orchestrated well? Obviously you want this to be fast and efficient. So you have asynchronous execution, tools 3 and 4 run at the same time, retry logic, replanning, durable computing for long-running tasks. So this slide here, can be a whole multiple talks in and of itself. This is a very rich space, but we're going to assume for a moment at least that this is all just a nice simple box. And one of the constraints, of course, is that these tools are hard coded at design time. Right, so many of us have used coding agents, and you have to specify the MCP server before you submit your query, right? Which means that the list of tools are fixed at runtime. So what I want to ask now is like, assume we have a single orchestrator agent, right? That orchestrator box is now everything we showed before, and more. So we're zooming out. Assume the agent exists. So it gets a query, decomposes it into a task graph based on available tools and capabilities. However, it identifies many capability gaps and must recruit support to complete the query. So the agentic web here is basically an environment where existing agents can coexist and they can, under the right conditions, recruit one another into coalitions to solve complex tasks beyond what any one of them could do alone. And such an ambitious vision requires tackling numerous engineering challenges. And the first is discovery. So in such an environment where millions or billions of agents might coexist, how can they find one another? And among all the agents that are discovered, how do they communicate and represent themselves and their capabilities? How does the orchestrator decide which agent's capabilities are a match for the task it needs assistance with? So to explore this, we'll discuss communication protocols, agent cards, and the semantic capability matching problem. Next, how can an agent prove its identity, right? Before connecting, communicating, and sharing information, agents should establish a foundational level of trust. We need authenticity, accountability, and privacy. And so in this section, we'll briefly cover the cryptographic trust architecture emerging for the agentic web. And proving identities is one thing, but proving capabilities is yet another, right? A person might present an ID proving they are who they say they are, but how do you verify that they can do what they say they can do? A human might have a diploma or a certificate saying this institution vouches for my capabilities, right? Or a review system for contractors like on Upwork, might maintain a ledger of past performances. And so looking at one, perhaps upon closer inspection, Agent F's reputation score is too low for the high priority task given to the orchestrator. So it removes it from consideration. And so now at this stage, the orchestrator can find agents, assess their capabilities through discovery, establish trust and authentication, faith through reputation, and can begin communicating and cooperating. But we've overlooked probably the most important question of all, which is why should an agent cooperate at all, right? It's operated by a different institution, incurring real costs, how should it prioritize its new request for work against its existing responsibilities for its host institution, right? So that's going to be the economics of the agentic web. And this requires tools from cooperative game theory, mechanism design, auction design, etc. And then, for example, perhaps during contract negotiation, agent G's bid for the work is too high, and so the orchestrator has to cancel that agent as well. So now it's deciding on the agents it can operate with. Um, and then even further, so once the coalition's been assembled and the work completed, the question becomes how should the coalition's value be divided amongst its members, right? This is the credit attribution problem, and it's not just an accounting exercise. The division rule chosen determines whether agents will cooperate tomorrow, right? So if agent B was called twice, as we see, while contributing to the coalition's goal, does that mean it gets twice the credit? Right. So we have now discovery, trust, reputation, economics, and attribution. But there's a final gap here, and that's that, suppose a dispute arises after the coalition dissolves. The orchestrator claims agent A delivered an incomplete report, and agent A claims it delivered a full analysis, right? And the orchestrator lost it or something. Without an immutable, tamper-proof record of what was actually delivered, the dispute is irresolvable. And so that's where we need accountability. All right, so that's kind of the roadmap of what we're going to kind of fly through here. So the question is, that we're built around is what if instead of, hard coding agent pipelines, we had a system where the network itself could self-organize at runtime, where agents that have never met before could discover each other, verify each other's identities and credentials, negotiate terms, form temporary coalitions, execute collaboratively, and then dissolve all of that when the job is done. That's the agentic web, right? And it requires us to solve problems that cut across, you heard it, distributed systems, mechanism design, cryptographic identity, semantic search, cooperative game theory. It's a very challenging and exciting space. So let's start with semantic discovery, right? So we've all heard of probably agent cards here. You can just think of it as an agentic equivalent to a DNS resource record, right? A DNS record tells you what the IP address of a natural language name resolves to, but an agent card tells you what an agent can do and how to reach it. So just as DNS decouples human readable names from network addresses, agent cards decouple capability from implementation. So a discovery system can find the right agent for a task without knowing anything about where or how it runs, right? And so, this definition here is agent cards usually hosted at this well-known endpoint in a JSON format. And basically, it is structured such that an agent A another agent can determine whether agent A can contribute to its task based on its descriptions and skills, and how to authenticate with it, and which interaction protocols it supports for communication. And as an example here's just two, very contrived examples that we might see in the health space. The IDs at the top there, they contain the new agent, :/ protocol. It's a URI-based framework for interoperable agents. It's been proposed in the IETF draft actually in October 2025, so it's pretty new. But the protocol field declares, which interaction protocols the agent speaks. An agent that only supports A to A, cannot directly be invoked by one that speaks only MCP 1.1, right, without a translation layer. And then the constraint block is important for coalition planning, right? If an orchestrating agent needs to know that, the clinical evidence agent can only handle 5 concurrent tasks before it decides to recruit it for a 12-task batch, right? It needs to understand its constraints. So that's great. An agent somewhere in the world publishes this agent card at their well-known endpoint, but how does an arbitrary agent find it, right? And so that's the idea of a registry. It's basically a service that indexes agent cards and exposes, a query interface to search through and find them. So agents register themselves at startup, or periodically, and agents seeking collaborators might query the registry with capability requirements. And so this is analogous to a service mesh control plane, or more loosely like a DNS root server. On the left there, you see the registry query. You say, what capability do you need? Clinical evidence synthesis. I want them to speak this protocol, and here's some constraints. And then on the right, after you perform that registry search on the request, you might get a list of agents. Here's agent ID, clinical evidence synthesis agent, the match score, the skills that seem relevant, and so forth. This is one way to search, but Two others is the idea of gossip exchange and broadcast, right? So the central registry is one way to index agents, but in a gossip protocol, agents that already know about other agents propagate that knowledge to their neighbors. So when Agent Alpha collaborates with Agent Beta, for example, Alpha learns about Beta's agent card and also about any other agents Beta has recently worked with. And over time, capability awareness diffuses through the network like rumors in a social graph. So imagine arriving at an academic conference knowing nobody. You introduce yourself to one person. This is the registry lookup phase. And then they say, oh, you work on causal inference. You should go talk to Dr. Patel over there, and she'll introduce you to the group at table 9 who are working on treatment effects, right? And that's gossip propagation. So your known agent graph expanded from one to potentially a dozen transitively without having any central directory that you needed to query. And then in certain environments and edge networks and deployments, local clusters, agents might announce their presence via multicast or broadcast, on a shared channel there, as you can see in Agent Epsilon. And that's just the fastest path to discovery, but it only works within bounded communication domains. So these are kind of three common ways that agents can discover each other via registry query, gossip exchange, or broadcast. So great. Now you've found an agent, but how do you determine whether it's a good fit for your task? So this is the challenge of semantic capability matching. And basically, you've got a relevance function M, which takes in a query and a capability and maps it to a number, 0 to 1. And the three criteria are lexical invariance, subsumption, sensitive, and directional and constraint aware, right? So these are the three criteria that such a semantic capability match must address. And so I'm going to focus on what those are here with examples. So lexical invariance in examples might be like synonymy, right? Evidence synthesis, is that equal to systematic review generation? There's no keyword match, but you need to identify whether those are relevant to one another. And the cross vocabulary is another problem. So you've got different people in different domains. Academics are pretty familiar with this, where you've got your own jargon specific to your environment. And now you need to communicate with somebody in a different field. Having the right vocabulary can be difficult. Subsumption sensitivity is pretty important, right? Because the idea is you might ask for a certain skill set, drug interaction analysis, and you need to know whether another capability that's being offered, pharmacokinetic modeling, is that a subset of drug interaction analysis, right? Can drug interaction analysis do everything pharmacokinetic modeling can do and more, or vice versa? Right? And then composability. Maybe you can't have any single skill that can solve a task, but you know that a couple of skills strung together can solve a task. And so composability, this is a very challenging aspect of the semantic capability matching problem. And then constraint awareness, HIPAA compliance, et cetera. You need to do some filtering on some basic constraints, which is important. And so as an example of how this is strung together, this pipeline I'm sharing with you is a novel application of the popular retrieve then reason frameworks for question answering and RAG style LLM reasoning. But I just applied it here to semantic discovery of agents, right? So each stage basically narrows the candidate set down while increasing the evaluation fidelity. So constraint filtering and embedding retrieval, they're fast there, millisecond. That happens at the top. Then you use an ontology for re-ranking when you're trying to do the subsumption resolution. And you bring all these scores together and you create like a reciprocal rank fusion type score fusion approach, whatever you'd like there. And then finally, you have an LLM as a judge, which is really important for deep reasoning and only on the final shortlist to give you the top K match. Okay, so this is just an example of how to resolve the semantic capability matching. You get all the agent cards, pass it through constraint filter, turn 10,000 to 800 agents, do some embedding retrieval, turn 800 into 20, do some ontology re-ranking to resolve the subsumption problem, go from 20 to 5, and then you use an LLM as a judge to give you your top K. Just here's some examples of how this has been emerging. Two papers and propositions have come out at roughly the same time here, both also IETF proposals. And they're proposing, the agent DNS is a structured place for agents to register themselves to be discovered. And then the agent naming service also is another paper that's out, right? We're not going to go through them, but just, promote awareness. This is a very actively developing space. All right. So skip that. So the roadmap, right? So now we've talked about semantic discovery. Now what about trust and identity? This is what we need to explore next. So we're going to put together a couple of layers. Often you talk about defense in depth. This is a kind of common posture in cybersecurity space. This isn't in my space, so I'm going to go through this pretty quickly just because I think it's important to be aware of the technologies here. So layer one is authentication. And so this is the decentralized identifiers, DID. So you can think of a DID, it is to an agent card what a passport with biometric verification is to a business card, right? So anyone can print a business card claiming to be, Dr. Smith, oncologist, but a passport, by contrast, is cryptographically linked to a biometric template that only Dr. Smith can produce. And the DID document is the digital equivalent. It's a public record of the agent's cryptographic biometrics, if you will, resolvable by anyone, but fakeable by no one. And this is just the first layer, right? But authentication alone does not establish authorization or qualification. So knowing that you're genuinely talking to, a clinical evidence agent does not tell you whether the clinical evidence agent is certified to make clinical determinations. So that gives you the second layer. This is where verifiable credentials comes in. And so the W3C, the World Wide Web Consortium, published verifiable credentials data model version 2.0 as a full W3C recommendation in May 2025, marking its maturation from experimental standard into a production-ready infrastructure. And so this is an active area that's live right now. And this VC is it's like a digitally signed attestation made by an issuer about a subject. And then it's held by what they call a holder and then presented to the verifier. So you have an issuer that gives it to about a certain subject. It's held by a holder and then presented to a verifier. So the nice thing about the way this is designed, though, is that it solves the attestation problem, but it introduces a new tension about disclosure. So if the clinical evidence agent presents its HIPAA compliance credentials, it reveals the full credential contents, including its operating organization, model version, last audit date, encryption standards, right? The principle of data minimization demands that agents disclose only what is strictly necessary. And so that's where the last layer comes in. It's kind of an emerging space, a very, very interesting space known as zero knowledge proofs. And this would resolve this tension. So a ZKP basically allows one party, the prover, to convince another party, the verifier, that a statement is true without revealing any information beyond the truth of the statement itself. It's a pretty profound objective there. So the ZKPs satisfy three properties. So completeness, an honest prover always convinces an honest verifier. Soundness, a dishonest prover cannot convince a verifier of a false statement except with negligible probability. And then zero knowledge, right, which is the whole premise, is the verifier learns nothing beyond the statement's validity. And so these three together give us the three-layer trust stack about agents, connecting and communicating with one another. All right, so we now need to move over to reputation, right? So the DIDs provide identity, the VCs provide attestation, and the zero knowledge proofs provide privacy preserving proof. But none of these mechanisms address the problem of tamper-proof record keeping. That's reputation. And that's where the block A to A architecture came to pass. So this is a proposal that addresses this challenge by recording critical interaction metadata on an immutable distributed ledger, right? The blockchain. So the key 2025 contribution in this space is by Zhu et al. Is this block A to A framework. And it was the first unified framework that formally integrates the blockchain primitives with Google's A to A protocol, right? The agent card, providing identity anchoring, immutable audit logging, and smart contract-based access control for full multi-agent systems. The identity layer on the left there anchors the agent decentralized identifier, the DID. The ledger layer provides immutable audit trails, right? So that's where the task state transitions are recorded. And then the smart contract layer enforces dynamic access control. And so together they provide a trust substrate for the A to A style multi-agent interactions. right? Because we talked in the beginning about the agent card, and then we talked about how to find them and how to search through them. And great, you found them, but we need that trust substrate bringing it all together. So this is a promising space because of how much work's been done already in the blockchain space, right? So on-chain operations, yes, they introduce latency, so we have to use this carefully. On the Ethereum mainnet, I think block confirmations take like 12 seconds or so. But on permissioned chains, right, it can be sub-second. But for the healthcare application prior authorization, for example, where decisions may have a 48-hour turnaround, even Ethereum's latency is acceptable, right? So it depends on the applications. But for real-time agent coordination, where you need some sub-second negotiation rounds, on-chain operations, they have to be asynchronous. And so the agent's log audit entries in the background after the coalition has already produced its results. And the key design principle here is basically using blockchain for accountability, not for coordination. And that's kind of the principle under the A to A architecture. All right, so we now have we've discovered agents, we've learned how to trust them and communicate with them, we have reputation, and this is probably the most fun area is the economics and fair credit, right? So there's kind of four pieces to this. Task allocation, which is, which agents should be recruited and at what price, right? Auction mechanics are required for this. And then effort elicitation. So how do you ensure that the agents exert genuine effort and they don't just free ride along to get some reputational credit that they can then use for some other task? This is the public goods game from economics. And then credit attribution. So how do you fairly distribute the rewards after the task has been completed? And here you can use Shapley values. And then long-term trust. So how do you build durable cooperation across tasks? And so we talked about reputation there. But staking is important too. So, in the staking environment, basically you have maybe a new agent that comes on board. And if it wants to participate in a coalition and doesn't have a large reputation, well, it needs to escrow, a large portion of its effort up front that it may then get back in surplus once the coalition's completed. But staking is a way of discouraging, free riding and helping, solving the cold start problem. And then, of course, once you get that reputation, that forms the information that will contribute to the subsequent rounds of collaboration. So there's a lot to go into for these, so I'm not going to go into all of them, but I do want to go into a little bit of depth with one of them, which I find very interesting, and that's mechanism design here. So mechanism design was formalized by Leonid Hurwitz in the 60s and 70s, and I believe it was recognized with the Nobel Prize in the 2000s at some point. Mechanism design inverts the standard game theoretic question, and this is what's interesting. In classical game theory, the rules are given, and then you predict how rational agents will behave. That's game theory. You're given rules, and you want to study how people act given rules. But in mechanism design, you flip it around. You specify the outcome that you want, the behavior that you think that they should follow, and then you engineer the rules of the game so that the rational agents would logically choose to produce that outcome, right? And you can imagine why this is so critical for agents, right? You don't want them to do things that we didn't intend for them to do. And so this is a problem of mechanism design. We have to structure the rules, bake in the optimal solution for these rational agents so that they behave the way that we expect. So the central question is, of course, can we structure the rules so that every agent's best move is to behave, honestly or favorably? And we'll see this with an example here. So let's look at two auction strategies. So each agent has an internal cost there and an external reported cost or bid. So this is going to be an auction taking place. So each agent, it has this private cost nobody knows about. This is secret to them, and they're bidding for work. And so let's go through one round here. Let's say agent one, to complete the task, it would cost them 100, and so they bid 100 honestly. Agent two, it's 110, they bid 110 honestly. And agent three, 120, and they bid 120 honestly. So in a first price procurement auction, what happens is you basically say whoever has the lowest bid wins. So the truthful bid of being 100 Agent one was awarded $100, right, to complete the task, and then they go and complete the task, which cost them $100, and they got a profit of zero because they truthfully bid what the cost actually was. Well, let's play the game again. And in this scenario now, Agent One bids more than they actually need, right? It's an inflated bid. And yet again, they still win. 109 is lower than the rest of the bids. And they're awarded 109, and their cost was 100, and so they profited $9. And then, of course, you can underbid here, which is not advantageous, right? If their cost is 100, now they might actually win, and they get $90, complete the task, and they actually lost money. So what's the problem here? I mean, the problem is that the first price procurement auction rules incentivize lying, right? It is the optimal solution to make more profit, right? There in the middle, you inflate the bid. If you compare the inflated bid to the underbid there to the baseline profit of behaving truthfully, and the truthful bid, you get zero, and lying is one way of lying by inflating the bid gets you more profit. Okay, so how do we solve this, right? Well, let's play the game again, but let's change the rules. So let's go back to the beginning where we have a truthful bid scenario, but now we're going to play a second price procurement auction, okay? And so in this scenario, they win, but how much are they awarded? Well, in this scenario, they actually get awarded the second highest bid. And so here in the second price procurement auction, the truthful bid, Agent One was honest and said, it might cost me 100. I'm going to bid 100. And so they bid that and they win, but then they get awarded 110. Their cost was 100. And so they actually profited $10. Let's play the game again and see, well, now Agent One lies and they say, oh, well, I'm going to bid 109. Well, what happens is they win because they're still the lowest, but their profit remains identical because they were awarded the second highest bid. Well, let's play the game again. And now they overbid 115 to see if they can, make more profit. And now they lose and they make zero profit. I mean, their award is zero because they didn't win. They didn't do any work, zero cost, so they get nothing. And you can play the game again and say, well, why don't they just bid really low and win? Well, because they don't know the true cost of other agents. In this scenario, if Agent Two's true cost was 95 and they bid truthfully, Agent One bids 90 and they get the second highest bid, which was only 95, and they ended up losing money again. And so here's the observation is that the second price procurement auction, there's the optimal strategy is actually to be honest. That is the way of maximizing your profit. If you look at the difference from all other bidding strategies, all of them either give you the same profit or less. You either get that profit, you make zero profit, or you lose money. And this is the idea of mechanism design. You bake in the structure and the rules such that the optimal strategy is to behave the way that you wanted and you designed. And this, I think, is a really critical observation when we think about multi-agent systems, which is, nice because they are actually rational. In the economic game theory space, agents are not, the human agents are rarely rational, but in the agentic space with AI systems, they're highly rational. Okay, so that's the takeaway lesson here, right? Cooperation must be engineered, not assumed. All right. And this work here is the problem from Vickery, Clark, and Groves. This is from the 1960s, and then Clark and Groves, in the 70s, generalized it to multi-agent systems. And so this is some really important economics work that's being used in this space. Okay, so that's everything. I'm going to go over the full picture here now, right? So at the very beginning, you've got an agent that has some capability gaps and it needs to recruit support. So we had that 4-stage pipeline we talked about, right? Which was, first you're going to do some constraint filtering, then you're going to do semantic match, and then you're going to do an ontology resolution, and then you're going to combine those scores and pass it to an LLM as a judge. And then you found some candidates. Now you need to establish trust. So you've got your decentralized identifiers for verifying authentication. You've got your verified credentials and zero knowledge proofs for establishing trust. And then the reputation on the blockchain ledger to keep track of transactions so that other agents can see what's taken place. Then you need incentivizations. This is the negotiation stage. And I gave you the example of the VCG auction just as one to kind of motivate the importance of this stage and how critical it is for effective multi-agent collaboration. And staking, which is, one approach for, solving the cold start problem. There are many others. And then once you have this here, you go into the coalition life cycle, right? You decompose, find some problems, recruit people, execute, and then grow, shrink. Maybe one of the agents finds another capability gap, reports it back to the orchestrator. That orchestrator then goes back to stage one, semantic discovery, trust stack, and keeps going, and eventually dissolves the coalition. And then you need to do the credit attribution at the end with techniques like Shapley values, which is there at the very bottom. Shapley value attribution and then settlement, the escrow account and resources are all resolved. Okay. So there's a lot of unsolved problems here. It's a really challenging space. Just as a couple of examples, credential revocation at coalition speed. How do you handle that? And then Shapley for dynamic membership. Well, what if a member joins halfway through? You want to do an honest attribution of their effort when calculating their Shapley values. Privacy preserving discovery, as we talked about, the zero knowledge proofs can be important, but there's a lot more under the hood there that we didn't dig into. The cold start problem, I hinted at, using staking as one way of addressing that, but there's many others because oftentimes you can't even get into the candidate pool unless you have a high enough reputation to let alone be able to stake to be considered, a competing candidate. Yeah, so the VCG was really interesting, but there's still collusion problems. That there's ways to break it, as I'm sure you can imagine, right? If you have two agents that are aware of the second price auction mechanics, you can have them bidding in a particular strategy that allows them to circumvent the system. You also have things like retirement attacks, where you have an agent goes out there for a month and just does great work, establishes a great reputation, and then just defects at a really high value job, stealing a bunch of money, lying about their capabilities, and then defecting. And then evaluating the evaluator, right? So, you've got this orchestrator, you have, Shapley's being calculated. How's that audited? Who looks over that and make sure that that's fair and regulated, right? So big picture is, we were asking ourselves, what if the network itself could form, grow, shrink, and dissolve in response to the task? And we have now some of the architectural foundations for that, or at least an appreciation of the challenges that we have to confront. Discovery, identity, trust, economics, attribution, accountability. These are all the building blocks. And I think what's important to think about is the agentic web that we want to work towards. It's not like a product. It's basically an infrastructure problem. And I hope I've convinced you today that it's solvable, right? The pieces are there. There's a lot of really promising work. We just need to keep pushing and start tying it all together and formalizing these things. So that's my talk. Really appreciate your attention, and I hope you guys learned some stuff.
That's it, David. So I have
Yes.
3 minutes for questions. So
Yeah, absolutely.
any questions?
Hi, thank you for the talk. I just had a quick question. Do the DID and the bidding steps suggest the need for for example, like a cryptocurrency to be used among these agents as part of like the smart contract system and for?
Yeah, so I didn't have it in here, but look up the Agent Exchange. So that's a 2025 publication that's basically trying to create, think of it like the New York Stock Exchange, right? It doesn't actually do any, it doesn't actually handle or store any of the money. It's basically just the infrastructure to support the exchange. And yes, as you suspected, cryptocurrency is one of the core components of how everything works. I mean, it's on the blockchain, and the cryptocurrency lives on the blockchain as well. So there's a lot of merit in trying to align those technologies. So I think the succinct answer is yes, there's definitely a need for that. And I encourage you to look up the Agent Exchange for some leading ideas as of 2025 on how that's being thought. Yeah.
One quick question for you. So do you think the agents need to talk in natural language, or do they need to invent their own language?
Yeah, that's a really fun, a fun thing to think about. I think there's kind of two ways to think about that. One is objectively, if you really just think about it from like an information theoretic lens, certainly not in the sense of at least just efficiency in communicating and solving problems, right? I mean, just look at the various languages that humans have invented and their similarities and dissimilarities. And so agents can most certainly devise more efficient forms of communication to solve their tasks if we were to allow them to do that. However, there's a lot of problems that arise, with transparency, auditability, and understanding what's going on under the hood. Maybe if we did allow them to do that, we'd have to have a critical translation layer on the top, but who's to say that that couldn't be circumvented or something. So yeah, just the two pieces. One is I think fundamentally, theoretically, that they can probably operate faster and more efficiently if we allow them to design their own languages. But I think there's a lot of considered costs that we should be thinking about that we would be confronted with if we let them do that.